Quick recap of what we did last time. Our basic filtering that model was this. The input was a 0 mean random process xn, okay. W0 to say W capital N with the filter taps. We are going to filter it yn filter such that if you take the difference between the filter output and the desired response dn, the error en, it's also random process 0 mean, because dn also 0 mean, its mean square value variance should be minimum. That we saw to be a quadratic function of the weights, and therefore, you can minimize them by differentiating that mean square value of the error with respect to each weight and equate it to 0, and you get a solution, which in this case gives minima. You get the optimal filter. Optimal filter was W opt was R inverse P, R was E of x n x transpose n, all real valued case, that is why it is transpose only, no Hermitian transpose, and P was d n, cross correlation vector. Then we said that since it is a quadratic function, suppose I do not know how to compute inverse of a matrix, but since it is a quadratic function, it has got only one minima. If you really plot this quantity epsilon square, which is the variance, and remember variance is independent of n, that we have already also shown. Okay, when you took out the expression for E n and replace this by square n and all that, n disappeared because of stationarity and joint stationarity between x n and d n. Because where the joint stationarity comes, you see this p vector is independent of n. There is a correlation between x n vector and d n, but it is independent of n, isn't it? So, because that is the joint stationarity. So, we said that time that since epsilon, if I plot epsilon square in an n plus 1 dimensional space where one axis is epsilon square and other axis, each of other axis is one weight or other, then it will be such a function that has only one minima, and everywhere else it will be going up, up, up. It cannot have local maxima, so it only can go up. Like in the simple case of single tap filter, it can be something like this, a single tap filter, that is this could be the optimum. It can only go up, up, it can never be like this, it can never come down. If it tries to come down, there will be a local maxima formed, which cannot take place because it is a quadratic function. If you minimize, if you differentiate it with respect to the weight, you get only a linear equation with one solution. So, it will go up, up. So, if that be the case, then we can follow an iterative procedure. We said, that is, suppose at ith step of iteration, we are having some weight. So, that time we find out the gradient here. If the gradient is positive, no point in going to this side, because we will be going further away, going the opposite direction. If the gradient here is negative, go in the right side. That means, you go in the opposite sense of the gradient. If gradient is increasing, you go in the opposite direction. If gradient is decreasing, go in the same direction. Okay. So, from that we derive the steepest descent algorithm. From Wi, we said we will go for Wi plus 1 by going against the gradient. So, we did this, this is what we did. This del is a derivative operator, it is nothing but just a vector form, where all the partial derivatives of epsilon square with respect to W0, W1 dot 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 are put one after another in a vector form. That derivative, there is a gradient. Here this figure was only for one variable. When you have multiple variables, multiple tap weights, then it becomes a vector of partial derivatives, and that you are evaluating at the particular iterate W equal to Wi, and from the current iterate you are subtracting. So, the gradient is positive, you are going in the opposite direction. If the gradient is negative, you are going in the same direction, and mu by 2 is a proportionality constant, mu is called a step size, and then we simplified it, we knew the formula of gradient which we worked out the last time, and what we got was this mu into P minus R W I. This is what we got. Okay. But this is still an offline, this is still an offline procedure, because given the P and R value, you will just do it iteratively sitting at home. Then I wanted to say that I want to do it in real time. So, first thing was to replace index I by n. So, at every clock cycle, I have one, step of iteration. Okay. So, 0th clock cycle, 0th unit of time means that time I am doing the 0th initial state, then first cycle means first iteration, second cycle, second iteration, like that. So, I am writing that offline this procedure iteration, but in real time. Even then it is not adaptive, it is because you are still using the given value of P and R, but suppose that is also not given. Then I said that R and P, normally what is R? After all, if you want to estimate R, it will be, what is R? R is expected value of x n into x transpose n. So, you should take one x n vector multiplied by x transpose n, take another vector, say x n minus 1. What is x n vector? Starts at x n, then x n minus 1, x n minus 2 up to x n minus capital N, is not it? X n minus 1 vector, it will start at x n minus 1, n minus 2 dot 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 x n minus capital N minus 1, so on and so forth. So, you take x n vector multiplied by x transpose n, take x n minus 1 vector multiplied by x transpose n minus 1 dot dot dot, maybe you do it 100 times, and then add and average, divide by 100, that will be a good estimate of R. Similarly, for P, but I said that suppose I use a weird estimate, I just do not take so many, I take only one. So, R I replace by only this, and let us see how it works. And suppose P I replace by x, if I can still prove that the convergence to optimal filter in some sense will work out, will take place, then I am through. So, if I replace this from this, I will not show the derivation, it is very simple, x p u replaced by x n into d n, or x n into x transpose n, x n and x n take out mu into x n. So, d n minus x transpose n w n, x transpose n w n is same as w transpose n x n. In this case, they become actually function of n now, which is the filter output, and d n minus filter output is error. So, what we got was the LMS algorithm. Okay, that is where I stopped last time. So, I start from that today. So, for the n plus 1th cycle, iteration cycle or time cycle, the filter weight vector is w n plus 1, that you get from w n by this. You understood how it came, na? You replace P by x n d n, or by x n x transpose n, take x n common, that is why this x n is coming up, and then within bracket this d n first minus x transpose n w, which is same as w transpose x, w r n, and w transpose x n is same as y n. So, d n minus y n, which is e n. So, this is algorithm, but that means what are the steps? This is one step called weight update, filter coefficients also called filter weights, weight update. But before that I must have E n, is not it? So, what is E n? E n is d n minus y n, and therefore, I must have y n. What is y n? Y n is in terms of given w transpose n x n vector. Okay. So, it is like this for n equal to 0 to say some final, and then you start this iteration with some initial value w init. Normally, we take that initial value of the this weight iterate to be 0 vector. Okay. This is the LMS algorithm. There are two main operations. One is the filtering operation, another weight update operation, which consume computation. Okay. We can draw an architecture for this, maybe sometime later I will do. In another class, I take the architecture and then pipeline and make a faster version, but here I am not doing, but I might do it. Okay. This is the most celebrated algorithm, spend some time on it. This is called the LMS algorithm, basic LMS algorithm. It is by far the most popular algorithm. In 80s, another class came up, totally defined in approach in derivation called recursive least squares, which gives more accurate estimate, faster convergence Like here WA, you will go on iteratively, we will show that it will converge, but that algorithm RLS recursive least square gives faster convergence, but that has some problem in structure and all that. Okay, it's not easy to implement. This is by far the most popular, even this has stood the test of time. Okay. This algorithm, you see, if I indeed had followed the exact steepest descent, maybe changing I to n also, does not matter whether you are doing offline with iteration index I or online with iteration index n. As long as you are doing this equation, this is the exact steepest descent, exact P, exact R. Then obviously, for proper choice of mu, you understand, you will go like this, you will hit upon this. That is, the filter weight will directly converge on the W opt directly. The error between them will be exactly 0, it will exactly become equal to that. But you have understood that I have not given you exact P, exact R, I have brought in some weird estimate. So obviously, after that the algorithm that you get, you cannot expect that to behave like the pure steepest descent, isn't it? So there is some compromise, but still that will converge. This convergence proof I will work out little later, but it will converge in what way? That if you take, see, Wn after all is generated in this algorithm from data. So Wn also is a random process. Wn also is a random process, because every time suppose you run the iteration, so from 0 to say 500, you get a sequence of W, W0, W1, I mean W vector 0 for iteration 0, W vector 1, iteration like that, you get a sequence. Next time again you run the algorithm, you get a sequence. So you do not get the same thing, because data is changing. After all, these weights are generated by data. You put initial vector, 0 vector, this data comes up, that generates the new vector, new weights. Put that back, again new data vector. So basically, filter weights are driven by generated by data. So that is a random process. So in that case, so if it is a random process, in that case, what I suggest that not suggest, what happens is this. Ideally, I would be very happy if I could show that as n tends to infinity, this vector converges to W opt, isn't it? But it will not happen, because obviously we are not following the exact steepest descent. So what happens if you take the expected value of Wn? What is the expected value of Wn? At each index n, you have got a set of filter weights. Take a particular one, say 0th filter weight. Just take that only separately. That particular one for the chosen n is a random variable, whereas next time you run the algorithm, you will get some defined value for that n, for that filter weight at that index. So, it is random. So, every time you do this, it will be fluctuating that particular filter weight at particular index n. So, it has a mean, then go to n plus 1, again at n plus 1 that filter weight will have some value for this run of the experiment. Next time we run again, its value will fluctuate. So, it will have a mean. So, the mean will converge. This can be proved, that this will become W opt. That means, this will prove. That means, suppose you consider only one tap filter to start with, only one tap filter, and this is your W opt. Only one tap filter, this is time index n, this is your W opt. So, this is your W opt. Okay. So, maybe this Wn, it is a fluctuating thing, maybe it will be fluctuating like this here. So, its mean is here, not on this. Then after a while it is fluctuating maybe here, its mean is here, so and so, maybe here, maybe after a while it will be here, maybe after a while it will be here, but finally it will like this. Okay, this much we can prove, but that is not enough. Obviously, you can ask the question, even if it convergence in mean, if it fluctuates like this, then what good it is? Then next time after that, we have to consider the spread, the variance also, then we will see how the variance will be kept bounded. That is a very lengthy analysis, but I am afraid I have to carry it out, very lengthy kind of boring analysis, lot of term, lot of very messy statistical analysis, but you would also get a flavor of how to carry out those analysis. That is a very, that might take 1 or 2 days in fact, that I will do later. Okay, there is a mean square error analysis, but this proof is very nice. Now, before I do that, I come back to more general case now. So long I dealt with real valued optimal filter, steepest descent, LMS. Now, I want to go for more general case of complex case. that is xn is complex valued, xn complex valued. Other things are same, complex valued, 0 mean, WSS, those are fine. And given R, which is now a complex matrix by Hermitian always, it is E of xn vector into x Hermitian. Xn vector is the same as original one. I am not changing the definition of xn vector, only thing is that xn now consists of your complex valued random samples, okay, more general case. Also given P xn d Hermitian n, which is same as d star n, because d is a scalar, no question of transposition. So, d star n you can put conjugate in, these two are given to you. Obviously, the filter weights also will be complex valued, yn complex valued, but 0 mean, because it is 0 mean, dn also complex valued, and therefore, en also complex valued, fine. Now, we will introduce we will have some notational things, I mean, we will introduce some notation. You should have, you put W0 dot 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 say Wn as your filter weights, isn't it? And they are complex valued in this case, in general, because I am dealing with complex data, this is complex valued. But instead of putting W0 to Wn in the filter, let me take their star values. Okay, it does not matter complex. What I am trying to say that I will in the end find out what is W0, what is W1 dot 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 what is WP, Wn sorry, this vector I will find out. If I find out W0, you know what is W0 star, you know what is W1 star, you know what is Wn star. So, I will find out W, I will find out the optimal filter version for W, but in the filtering I will use W star to Wn star, there is no problem, no. This is the notation thing I want to make clear. My purpose is to construct the filter. You could otherwise put W0 here, Wn no star, and instead find out W0 star, W1 star, Wn star, because that is how the derivation is. The derivation will take the conjugate of this and find out. But after you find out, you can construct the filter. So, either you remove the star here, bring the star here, we put the star here and find out W. Once you find out W, you know what the filter is. Okay, this is just a notation. So, that means if this is W, what is Yn here? Can you tell me? W what times Xn? W Hermitian times Xn. That is the thing I want to do actually. If I let us call this W, in fact, let me not bring n here, because so far it is not adaptive. Only when it becomes adaptive, then I just brought in the index n and all that. So, to start with, it is not adaptive, just I am trying to find out what are the optimal set. This is an optimal winner filter. So, some W I start with and WH. So, Yn is WH Xn, no problem, because this is my W and I said in the filter there will be star. This is just a notation, nothing else. There will be complex valued coefficient. You can either take them to be the way they are, you can take them to the conjugate of some other variables and find out those variables. W0, W1, and once you know W0, you can construct W0 star, W1 star, dot dot dot. Okay. Essentially, whatever you have here, you take the conjugate of that, form a vector, the derivation will give you that vector. That is how the derivation is. But there is nothing wrong. Once I know the vector, I also know the filter weight, just have to conjugate, that is all. So, Yn is this. Epsilon n, this time not E square, this time it will be mod En square out of complex, and mod En means EAHN. Okay. Mod En square, scalar number, so E and E star is same as En and EHN, and now you have got same quantity with Hermitian. And now expand. If you expand d and d Hermitian, that will give you E mod dn square, which is the variance of dn, because dn is a 0 mean process. So, mod dn square expected value, that will be the variance, you can call it sigma d square. It is of no importance to us here, because it does not depend on the filter weights. After derivation, this will go. The two cross terms earlier were same. Now, this time they will not be same. One is the conjugate of the other. Earlier, this conjugate fellow was not there. I will repeat it. So, the two cross terms were same. Now, this, because of this, I have to write the things directly. Okay, WH xn d star n E of that minus E of dn xhn conjugate xhn w plus other term. Pretty simple. And you see, E will work only on this part or here only on this part. W is not random. Okay, I am just trying to find out a particular set of W which is optimal, but W is not random here, unlike the LMS. Okay, W is just a constant, I want to find out. It is an unknown constant. And here also E will work on this. So, obviously, here you will get E of xn into d star n means the given P vector, and here you will get P Hermitian. E over this is P Hermitian. If you take the Hermitian of this, Hermitian after expectation or Hermitian before expectation, then apply E, you will get the same thing, isn't it? You make it row and conjugate and then E, or you take E and then make it row and conjugate, will the same. So, expected value over this means P Hermitian times W. Okay. And here E will work on this part only, which is R. So, W Hermitian R W, sorry, there is no N, I am again making a mistake. So, if you do that substitution very quickly, sigma d square minus P, sorry, WHP minus PHW minus WH or W. Okay. This is epsilon square is a real quantity, no doubt about it. Also, it is independent of n because of stationarity, as you saw see in R and P, no n is there. It is a real quantity, but it is a real quantity is a function of a set of complex numbers W0 to Wn or W0 star to Wn star, which one you want to see? You want to see this way or that way, right? Each complex number has got both a real part and imaginary part. So, actually there are 2n number of 2n plus 1, 2n, how many here? 0 to n means n plus 1. So, twice that many, 2 into n plus 1, that many variables, real, imaginary, real, imaginary. It is a real function of 2 into n plus 1 number of variables. Each complex number has got 2 variables, and then I have to to find the minimum, I have to differentiate it with respect to both the real part of each complex variable and the complex part. Again, real part of another complex variable, complex part of that variable, so and so, isn't it? So, it is more complicated than the previous case. Now, before I proceed further, you keep these results. Let us do some again, let us come back to some basic matrix facts and all that. Suppose I have a function epsilon square, general function. It is suppose a function of say one random variable z, and z is say x plus jy, but epsilon square is a real function, that is very important, very important. And I am to find out del epsilon, the minima of this. This also given it is a quadratic function or some function, that is a minima. I have to find out the minima or maximum, whatever. I have to differentiate it and equate. That means I have to take del epsilon square del x equal to 0, del epsilon square del y equal to 0, isn't it? So, if I instead I form a definition of del epsilon square del z. I don't know if this is correct or not, this notation. Okay, strictly mathematically is correct or not, I don't know, but suppose I just define it. This is equal to del epsilon square del x, differentiate with respect to x, also differentiate with respect to y, and put a j here. And then if I equate it to 0, even then this will be 0, this will be 0. 0 means complex 0, 0 plus j into 0. Isn't it? So instead of having two equations with this definition, if I proceed with this, if I proceed and equate to 0, still I will get the same minima. Okay. Then suppose epsilon square is not a function of z, it is a function of z star. Still it is a function of real function of x and y. Suppose z star comes here in this function, but finally it is a real function. So still again it is still a real function, okay. But still function of x, y only, and again I want to find its minima. So again I have to do this del epsilon square del x equal to 0, del epsilon square del y equal to 0. So even if it is a function of z star, if I use the same definition, and equate it to 0, I will still get the minima here, because after all I am interested in this being 0, this being 0, isn't it? It does not matter whether it is a function of z star or z, essential thing is it is a function of x and y. I have to minimize it, I have to form del epsilon square del x equal to 0, this also equal to 0. So even here if I make this, use this definition and equate that to 0, I will still get the same minima, isn't it? Even though it is not f z but f of z star. So even a function which is a function of z star, if you want to find the minima, I have to take the derivative of that as per this definition with respect to z, not this complex z star, but z, and equate that to 0. Nothing will change, I will still get this equal to 0, this equal to 0 means the required minima point, because after all it is a function of x and y only, a real function. Only thing is if you want to find out which j star, you should say okay, x minus jy, that much j star. At that z star, this is minima. When you talk in terms of z or z star, then we say it is a function of z star, and at z star equal to this x minus jy, this will have minima. But in terms of x and y, there is no problem. Even if I differentiate with respect to z as per this definition equal to 0, I will still get the same solution for x, y, isn't it? Then if you say that okay, at that z star, at which z star this is minima, you say form this x minus jy, at this z star this is fine. If that be the case, using this definition, you see some nice things. Suppose I give you two real numbers, scalars, but complex valued, a and z. A is a complex value, z is a complex number, a into z or z into a. And I say you differentiate this with respect to z as per this definition. What will that be? As per this definition, you write z equal to x plus jy. Okay. So, ax, a I do not need to expand because it is a constant. A is complex, but I do not need to expand. Ax, you replace z by, I am not showing those steps, or should I show those steps? A into x plus jy, isn't it? Now, apply that definition. This quantity, if you differentiate with respect to x, this quantity with respect to x, with respect to y. If you differentiate with respect to x, you get a. If you differentiate with respect to y, you get j into a. And there is another j here, j into a. So, you get 0.
But those two you define for real functions, and you said initially that epsilon square is a real function. Will that have any effect?
This you can extend here also. What is the problem? Even if it is not real, it is a function, okay. I mean, I stuck to this because that error was real, but if you just consider a into z, this is a good question, a into z. Okay, if I extend the definition here, this can be extended. I mean, I don't see any problem. This is my definition on complex derivative. whether it is a real quantity or complex quantity, differentiate like that. Because on the left hand side I will follow that. So, I have to do the same thing on each of the term on the right hand side. Okay. On the left hand side, if I do that, I will do the same thing on each term on the right hand side. But because of bringing this j and all, actually this is a smart mathematical trick, nothing else. The bringing by j here, you can make this cancel by clubbing the 2 and bringing a j. Okay, some simplifications. So, it is just a mathematical trick, nothing else. On the other hand, if it is not z, but say a into z star, a into z star, then that means and you get a and plus j times minus j a, isn't it? So, you get 2a. Again, mind you, this is purely my construction. I constructed a definition. I am not deviating from my original goal of minima, because ultimately it was partial derivatives, whether you want to write them separately equal to 0 or under the same banner, if club them like this and equal to 0, you will hit upon the same minima. Because our target is get that minima. As far as that is concerned, we are not making any change, mind you. I am only doing some jugglery actually, some mathematical manipulations. I brought in a definition so that in some cases this cancels, in some cases you get 0, you get twice a. That's all, isn't it? But essentially, I will be taking the derivative of that with respect to real part, imaginary part, all the weights equal to 0. I get some solution. The same thing I will get if I take del epsilon square with respect to first weight as per this definition equal to 0. With respect to second weight as per this definition equal to 0. Because there also you can separate out these parts, real part, imaginary, that is the solution that we will get. Okay. But by clubbing this is a mathematical trick I am applying to get some of these nice things, which result in simplification in a complex case. Okay, that is it. So, if that be the case, now let me extend it little bit. These are just scalars. Now, suppose I have got some vector. So, some vector W Hermitian, some vector P. That is W0 star, W1 star, say WK star, WN star, dot P vector. P has P0, P1, P2 like that, okay. So, this is a function of, earlier I took that case of Z star and not Z. Here also, this thing is a function of the conjugates of the complex number. Earlier I had only one scalar complex number, I took either that number itself or star, Z or Z star. Now, I have got one number here, another complex number here, another complex number, it is a multivariable case. But suppose I want to differentiate these above with respect to a particular one, WK. Okay. Firstly, others will go, only you have to hit upon these. Others will go, isn't it? Because WK. So, WK star and from here PK will come up, kth term, WK star PK. So, this will amount to del WK star PK, two scalars divided by del WK, I mean this not divided by, never assume that dx dy means dx divided by dy. And this we have seen is twice PK, isn't it? When you have star, there is no problem, no 0 comes up, twice PK. Obviously, this means del W that is one. If on the other hand you have the other term P Hermitian W, do I have to do it or you can see yourself? If you do this, take the general term, because P Hermitian means P0, P1 dot 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 all star multiplied by W0, W1, take the kth term, because you are differentiating with this to WK, only the kth term, so that will be PK star WK. That if you differentiate with this to WK as per the definition, it will get to 0, isn't it? So, this will be a 0 vector. one result, another result. And the other thing is, now you take this quantity W Hermitian or W. That again I follow the same procedure as I did earlier. What is this? Odd W is a vector, W Hermitian is another row vector, column vector. So 0th into first element, second element, second will like that. 0th element, all you multiply and add. So that means I equal to say 0 to n Wi, but because it's Hermitian, W star, isn't it? Wi is a row vector star, so Wi star, and whatever be the odd W thing, ith element of that. Absolutely same steps. Whatever the odd W vector, ith element of that, and ith element of this guy star, and you sum. This is the meaning. And then what is odd W? Its ith element means ith row of R times the vector. This is a matrix, this is a vector. So ith row of R times the vector, that will give the ith element of this resulting vector, isn't it? Or ij wj. And now suppose you want to differentiate this, you want to differentiate this quantity with respect to wk for a particular k. Then as before, I will take the summation I equal to 0 to n, out of that I equal to k, that case will be separated out. But I not equal to k, you can see this, no? And then the k, I equal to k case. I equal to k means kj wj. Okay, I have to differentiate this with respect to wk. So here wk does not occur, but for each wi star, there is a summation in which wk occurs when j equal to k. So that times I have rik wk. rik wk. Rik could be complex or real, I don't care. Rik wk and wi star. So wi star rik is together as a constant independent of k into wk. If you differentiate, you get 0 because no wk star. Are you following? So these are the advantages I get by virtue of that trick I applied. This was not there in the real case because j factor was not there, so I could not bring in j and multiply j by j and have something cancelled and make 0, isn't it? This is the mathematical ingenuity. Bring in j and make it compact. Otherwise, I could carry out the derivation with every real derivative with respect to real part even separately and a more elaborate exercise.
So we will get the same result even if we carry.
You will get the same result. Agreed. You will get the same result. Result will be same. Same winner expression will come up, isn't it? Provided I followed this model, the W star here and W and this W I am finding out, not W star I am finding out.
So this differentiation you can also do using what we call chain rule, like once you
That chain rule thing, I know. If you then I have to prove that chain rule is valid under this definition. This morning I was thinking, then I thought that okay, first I have to prove it. Due to paucity of time, I could not work out the proof, so I thought of going down to the basics. But if you want apply the chain rule, what he's saying is that if you have two more products, fx into gx derived with x, then fx into g prime x plus f prime x into gx. Same thing you can do here. W Hermitian RW. RW is a vector. W Hermitian is a vector. Hold down RW whole, and then multiply. I mean differentiate WH with respect to WK and whatever, and vice versa. But then that theory, that derivative of fx gx is f prime x gx plus fx gx prime. So I have to prove that that is exist, that is valid also in this modified definition of. So, since I did not do that, I am deliberately keeping it, okay, avoiding that. I am aware of that. One book, that Farag's book does that, I remember now, but he does not prove that part. He assumes that that theory extends to this definition also. It will, but since I am not proving, I do not want to, I mean, do things where there is a mathematical gap, that without proving some particular theory and all that, I do not want to use that result. So, that is, there is no point in, there is nothing wrong if I do this elaborate exercise. So, this part goes to 0, all of you agree? This part will go to 0. Now comes here. So, this part I work out separately, W k star once again, if you take out the k separately out of the summation, what you have is j not equal to k wj plus j equal to k case or k wj k here, wk star here, which means mod wk square. Okay. First differentiate this. First differentiate this quantity here. This quantity is to wk. Obviously, twice this will come up, isn't it? That is del will then reality what? First twice this will come up. See, what I do, you will not find any gap mathematically, It might be looking little elaborate. R k j w j, and here mod w k square. Mod w k square, you see, if you differentiate, after all, what is this? You forget about this. Once consider z is a function of x and y. Z is x plus jy. Mod z square is x square plus y square. So, if you differentiate with respect to x, you get 2x. With respect to y, 2y. So, put in that formula 2x plus j 2y. There is 2 into z. So, same thing 2 into wk will come up. 2 rkk wk, and now you combine the two. K was missing here, k has come back here, k case, isn't it? So, this is twice rkj, j from 0 to n w j, and what is this? Kth row of r, you are scanning the row. Kth row, j equal to 0 means first column, j equal to 1 means second column, and multiplying also simultaneously by this. So, kth row of r times this vector or w, that will give you derivative with respect to wk. So, with respect to other w's also, other rows times the vector. So, that means if you want to do together in the del form of that factor w transpose, sorry, w Hermitian or w, what we will get is twice r w. This will give rise to w vector. This was the kth row. So, k, it could be first row, second row, third row, depending on the choice of k. Putting all together, it becomes twice r w. So, now we put back in that formula, derive the full filter. This is what we were. This is where we were. Okay. And we have to differentiate this with respect to, that is del. I have to apply now del. Del epsilon, I mean, I shouldn't have written epsilon n, because it is actually, you can see now, that time I wrote epsilon n because I did not prove stationarity, but you can see it is independent of n. So, now we back to epsilon square. So, you have to apply del epsilon square with respect to w. This will go independent of w. This is going, no, this is not going, this is giving rise to 2p, isn't it? This is giving rise to 0. This is giving rise to, and this is plus. This is giving rise to twice r w. That is equal to 0. That means will give rise to what? Twice r w minus twice, from here you get this part, twice p, and that you equal to 0 vector. Obviously, you will get that optimal filter same as before or inverse P. Only thing is don't use this filter, but use the conjugate components of, then things will work. So, in a complex case mind you there is a difference. Actually filtering you are not using this optimal one, but conjugate values. Okay, but you are evaluating this, you get the same expression.
So you could have also taken D as complex. I mean,
I have taken Dn complex.
D you could.
Who is D? This Dn. Dn is complex in general.
No, I mean.
Who is D?
Forget myself.
Dn is complex. Everything is complex. I have taken mod Dn square. You see.
Yes, sir.
I don't know. I mean, everything is complex here. Zero mean. Stationarity is valid. Joint deal stationary, WS, all those things are fine.
In your real case, always the signals are in linear and real.
No. You can construct. You see, in communication systems, most of the modern modulations, they use two components, I component and Q component, and together it goes, isn't it? So that symbol is a complex symbol. When you transmit, okay, basically you transmit one waveform, but when you recover the signal out of it, there is a two component, and they are treated in the complex variable way, I and J, isn't it? So there, if you want to develop an equalizer, you have a complex equalizer, which will be like this. Complex cases are our construction for our convenience.
So earlier we got, like, now you have differentiated one place we are getting 0 and another place 2 here. Earlier we got A and A in the real case.
That both are absorbed in one here now.
And one is
1 is 0. Okay. All right. So far is the I gave you the complex, more general case, complex version of Wiener filter. Now again I want to do steepest descent here. I don't know how to compute an inverse. I want to do steepest descent. Once again, epsilon squared is a real function of what? Of how many variables? 2 into n plus 1 variables. 2 into n plus 1 variables. Real part, imaginary part. Real part, imaginary, like that. So again there, it's a quadratic function of all those real and imaginary parts. So it has got a unique minimum, and everywhere it will be going up. So I can apply the steepest descent. So I have to take the gradient with respect to real part also, imaginary part also, for each variable, and going the opposite direction, isn't it? So suppose this is epsilon square. Suppose I have got only one weight. To tell you, I have got only one weight, W, which is say WR plus J WI, capital R, WR plus J WI. Epsilon square is a real function of this, but it's a quadratic function, isn't it? So at any iterate, what you have to do at any point of iteration, I have to differentiate with respect to, because it's a real function of WR also, WI also. So I have to differentiate with respect to WR, with respect to WI, and going the opposite direction, isn't it? Going the opposite direction. That means WR, I have to go in the opposite direction. So mu minus mu by 2 times this term will come up. So W real part, if you want to do real part, you want to update the real part, you should have things like this, isn't it? From ith iterate you go to I plus 1th by this, and this will be evaluated at W or equal to WRI, or you can put W equal to WI, doesn't matter. Because when WI, obviously it will be WRI. And similarly, there is no vector here, I am taking only a single case, no point in WI okay. But once again, instead of having two equations, I want to club them. My I plus 1th net weight is this plus j times this. Net weight, net filter weight, at the I plus 1th iterate, the net filter weight WI, I plus 1. What is that? WR I plus 1 plus J WI I plus 1. What was Wi? Ith iterate, Wi was Wri plus Jwii, isn't it? I dealt with them separately because after all epsilon square is a real function of both Wr Wi, so you go in the steepest descent manner, consider real part separately, ith to I plus 1th, imaginary part separately, ith to I plus 1th, and go in the opposite direction of the respective gradients. But suppose I don't want to spend so much of space, I have to write the two equations simultaneously. So I multiply this side by j, add, I mean left hand side and right hand side both by j here, and add from top, add with top. So what I will get on the left hand side total weight, here it is total weight, and mu by 2 is real, mu is real, okay, that is important, mu is real and constant same, important thing mu is same for the real and imaginary part, so that is common, and then use my definition del epsilon square del Wr plus j times del epsilon square del Wi, so that is same as del W at W equal to Wi, okay. So this is the underlying thing. I could as well have just written down this expression. I follow the same steepest descent procedure and go in the opposite direction of gradient, but that is not really mathematically very sound. I have to see what it is. This is not a function of, this is actually, this derivative is my creation. Actually, this epsilon square is a real function of so many variables, real part also, imaginary part also, and I must do the steepest descent on each. Then I am saying instead of doing like this, I want to combine them. And I guess this steepest descent thing is okay. So you can extend it Wi plus 1, the multivariable case, multi-weight case, Wi minus mu by 2, del comes now, okay. I can easily generalize this, I am generalizing, and this gradient also we have found out in the previous minimization procedure, isn't it? This is the gradient. You put that back, 2 cancels. So what you get is simply mu into p minus r Wi. And then to go to LMS from here, what do you do? You can first make it online by switching from I to N, but still you are using P and R, no real data, only thing you are running the data and looking at your watch, but I am saying I want to use real data and again replace R by xn x Hermitian n. Please see, R is not xn x transpose, xn x Hermitian n. Please see some difference now, and this is xn d star n, right? If you put them back here, you can see quickly Wn plus, I'll just finish in 1 or 2 minutes, plus mu xn d star n, xn d star n here and x Hermitian. So x is common, bring it out. In both xn is in the common thing, the first. So you take out xn, the x d star n remains here, minus x Hermitian n and w, but Wn now, I has been replaced by n. And what is this quantity? We know by what this definition WH x is y. So XHW is y star, Hermitian of y, when y is scalar, so y star. So this quantity is y star n, that means dn minus yn star of that, so E star n. So this is the complex LMS algorithm, E star n. Okay. Other steps are simple. Filtering step, that is write down the steps quickly, just it will take 1 minute only. You first find out yn, yn is WHN, mind you have to write WHN. Filtering requires WH into xn, En, dn minus yn. Next step is W, you have used current weight, now go for the next weight from this, that is mu times x bar n, x vector E star n for n equal to 1 to final n, and you can take some initial value. W0 is W init. Okay, so that's all. So that's all for today. This is a complex LMS algorithm. We'll start from here in next class. Thank you very much.